Good morning.
Okay, so as I told you yesterday, today we're going to have a different kind of course. I'm not going to make use of the slides. As I told you, I'm going to present you the basic stuff regarding the RTL methodology and how use this. Okay, and mostly I will use for this course Notepad++, okay, which is my preferred editor in Windows, and I am going to use Vivado tool from Xilinx to make some synthesis, to perform some simulations and so on. Okay, so the PowerPoint, the PDF, the slides you have on Virtual Campus, I'm not going to load them today, and as a matter of fact, I will also not going to have some courses will be without the PowerPoint slide as you have them on the virtual campus. Okay, if you have also, I would like this course to be a little bit interactive, so I will ask to do I will ask for you to do some coding, okay, and some examples, okay, because this is something that in this part it's much more easy to learn. Okay, so as I told you, we're having the RTL two segment. Two segment relates to the fact that you have one segment which is combinational, one segment which is sequential logic. Okay, okay, so the first question is what are the main characteristics of combinational circuits?
That they don't rely on a clock and their output is almost instant.
Okay, so first of all, don't take into account this kind of thing with the clock. Okay, the clock is, let's say, a synchronization signal. Well, it is the synchronization signal. Okay, so the first thing is there, if you don't take into the consideration the delays on the different circuits, okay, let's say the delays on the logic gates, the output change instantly with the change of the input. Okay, so they don't have any kind of memory, so the output is dependent only on the inputs, not on the so-called previous state of the circuit. Okay, and every change on the input leads to a re-evaluation of the function that combinational circuit implement, and this may lead to a possible change in the output. Okay, depending on the function that is implemented. Okay, so I will start with one of the most simple example with the decoder. Okay, okay, so let's say, just let me save it. Okay, I'm going to use Verilog. Okay, let's say, come on. Coder 2 to 4 decoder, okay? And let's say decoder 2 to 4. Okay, how many inputs does the decoder has?
Two inputs.
Okay, general decoder, how many inputs?
General decoder n inputs.
N inputs, and how many outputs?
2 to the n outputs.
2 to the n outputs, okay? So let's say we have, in this case, we have the inputs. Let's say input 1, 0. I will represent in a vector way. Let's say A, okay? Output, we have 2 to the power of 2, 4 outputs, let's say Y, okay? I'm gonna have here some comments, okay? So in the comments, I will have the truth table for the decoder. Okay, so if the inputs, let's say Y1 is 0, Y1, start from, okay. So which logic value do you want to be the active value for the output? 0 or 1? This is a matter of choice.
One, I suppose.
1, okay. So for 0, 0, which will be the value of the outputs? Does anyone knows?
0, 0, 0, 1.
Okay. 0, 1. Here the outputs will be
0, 0, 1, 0.
okay. So actually the value at the input will give the active output. Okay, so this is the decoder. Okay, so so that's the truth table, and now I'm going to implement in a combinational way. I will put here reg. This course is not about Verilog. I'm not going to talk about data types in Verilog, okay? So most of this, this is about design principles, and as you know, it's more important of what you code than, okay, it is also important how you code, but I'm not talking about this. Is not, I told you, it's not a Verilog course, okay? So however, I will insist, I am going to use an always block. An always block because it allows to use sequential kind of statements. Most of the code in HDL, it's concurrent, okay? And if I want to use sequential ways of sequential statements, I need to use either in initial, either in always blocks, okay? So for which is the input for the decoder?
A.
Okay, so first of all, I have the always block, and in the sensitivity list, I'm going to put all the inputs for that combinational part. Okay, so in this case, I will put A. Okay, then I will talk. I have here some form of initialization. Let's say I put something like this. Okay, based on the truth table, which kind of statement instruction that you use also in programming? Okay, for example, can be used to describe in a easy way the decoder.
The case.
Okay, so you use a case A, and here you have, and because it's very long, it actually doesn't matter here. Or okay. If you have questions. So, first question I will put, what is about this sensitivity list? So, this part, okay, here.
The output will change only when something in the sensitivity list changes.
Okay, so actually, the answer is correct. The sense is that the always block is, if you're going to think about from a simulation perspective, the always block is something that it's inactive, okay, and becomes activated when an event from the sensitivity list, and when I write something like this, means any change in the value of the A will lead to the activation of this always block, and the lines of code from the always block will start to, let's say, execute, to get evaluated. Yeah, so this is somehow similar to what happens in a combinational circuit, in the sense that you have the inputs. Here you see in the always block, in the sensitivity list are all the input signals for that specific combinational circuit described by that always block. Okay, so there in that any change in the inputs, and here I put in the always in the sensitivity list all the inputs for that combination block will lead to reevaluation of the logic function and the possible change for the output. Okay, so what I would like you to do now, okay, try to make okay, let's say very simple 2-to-1 multiplexer. Okay. So first of all, which are the inputs and which are the outputs? For a multiplexer, which are the inputs and which are the outputs?
The input, one input should be the select line.
Okay, so you have a select input, okay.
Another should be the actual input that has to be selected. So in this
How
case,
many?
2 lines.
Okay, let's say. Okay.
And then the output 1.
Okay. Okay, so the truth table. Or I will put something like this. Okay, the truth table. So what happens when select it's 0?
Y is D0.
0, and when select is 1, Y is D1. Okay, so I let you 2 minutes to try to code this multiplexer.
I have a question.
Yes,
For the previous example of the decoder,
yes,
the first assignment of Y,
yes.
isn't it redundant because we cover all the cases?
Well, let me tell you, in this case, it is redundant. Okay. I will give you an example of what happens if you don't initialize. Okay. And when the code grows bigger, you may not cover all the cases. You know what I'm saying? So this is, for this case, it doesn't matter. Okay. Especially if you have nested ifs within the case branches, you have to be very careful. Okay. And in order to prevent this kind of issues, I usually start with this kind of initialization. Of course, in this case, it is redundant. Okay. But I'm talking, I'm trying to talk about some things that, for example, when you have quite okay, big, when your project is substantial and you write lots of lines of code, okay, then you have some issues which are not apparent when you have like 30 lines of code, like in this case. Yeah. Okay, did I answer your question?
Yes, thank you.
Okay, someone is willing to share the screen?
I may share the screen, but I wrote in Notepad. I don't have a simulator.
As you have saw, I wrote in Notepad++.
Okay, and I'm not sure about the statement, but I
Okay,
think
so you can share.
this is
In this case, this is okay, a more difficult kind of thing. So I don't know. I didn't use like this. Okay. Can you stop share? Other examples? So try to go the simple way.
I mean, I could write an if instead of that.
Yes, you can write an if, yeah. And you don't have to put the ORs in the sensitivity list. You can go with commas, okay? And it's a signal actually on 2 bits, so you don't have to write the 0 and the 1. Okay, who is willing to share?
I have a question.
Yes.
Another option would be, instead of using an always block, to use something like
A sign.
sign.
A sign, yes, you can use. As you for the assign, yes, it's an option. However, if you grow on a, let's say, bigger if you grow bigger, you'll see that just a sign, it's not so trivial, yeah. Who is willing to share?
I can share.
Okay.
I'm not sure if the syntax is correct.
Okay, it doesn't. Okay. So yeah, that's the thing. Okay. Good.
Okay.
Okay. Good. So I'm gonna have a short simulation, just 1 minute. I'm gonna also write a test bench. Just okay. So so the test bench usually it's a module which has no interface. Okay, so you don't have ports. Okay, we have something to assign the inputs. And this and we're going to follow up the outputs. Okay, and first of all we have the module instantiation, and here we have the name of the instance. Let's say dut .a, it's atb. I usually when make instantiation, it's I usually use this point-based version. Okay, so on the port A from the deck to 4, I'm going to map the signal ATB. Yeah. And there is also the possibility of using, let's say, like in C or Java, when you call functions or methods, just to use the list of parameters. Okay, so here you use the list of signals, and it's on a position-based, let's say, assignment. Okay. However, I usually have designs which have something like 20 signals in that interface. So it's pretty easy to not to match the position or to forget one. Okay, so that's why I use this kind of okay, then I have on initial. Let's say I will start with ATB 0, then I will have some delay. It's another delay. And another delay. This kind of module allows me to do exhaustive testing, okay, which of course is not possible always, or it's not possible for big, large circuits. Okay, this is the test bench. Okay, I'm going to use Vivado for simulation. Okay. Do you see my Vivado screen?
No.
No? Okay, just 1 minute. Okay, I have also done the simulation in Vivado. So basically what I wanted you to show is that here you have the change in the input, okay? So the input from 0 becomes 2, and you have an instant change, okay? We're not keeping in mind the gate delays, an instant change in the output. The same as here, the same as here, okay? So this is about the combinational circuits modeling, okay? I will give you on virtual campus some examples. We'll have a very short break and 5 minutes break, and we'll resume with sequential circuits, okay? And then I will have a very short example of 2-segment finite state machine, okay? If you have questions. If you don't, we'll have a 5-minute break. Okay, so at 55 we'll meet again. Okay. Is it okay for you?
Yes.
Okay. Okay, so here again, as Arnold told, I'll be back. Yeah. Okay. Have you seen the Terminator, the first two Terminator movies?
Yes.
Okay. They were the classics of my childhood. Okay, good. So let's go back into uh, the course. As I told you, I will go with the sequential logic. So first of all, which are the main characteristic of sequential circuits? There are two.
They have memory and they use a synchronization signal.
Okay, so they have memory. Synchronization signal, it's not something specific to all sequential circuits, okay? You can have asynchronous logic as well, okay, although it is not used today, but there it is. First, they have the memory and they have feedback, okay? By the way of the feedback, you ensure this memory property, okay? As a matter of fact, the output of a sequential circuit, it's dependent not only on the inputs, as it was the case in combinational. The output is dependent on the input and the so-called state of the circuit, which most cases are the previous outputs, okay? And about the memory thing, I will give you a very short example. I will write in Notepad++. Okay, here, let's say we have a counter which counts till 4, so it counts this, and from 3 it goes back into 0, and so on, okay? So how do you know that you're going to enter into state 2?
You are previously in state 1.
Because you are in state 1, okay? So basically, this is the memory part, okay? Because the next state, okay, is dependent on the so-called current state, yeah? Okay, so in this very simple example of the counter, you have this, okay, you know the following state based on the current state. So basically, if you are in state 1, you will enter state 2. If you are in state 2, you will enter in state 3, and so on, okay? So this is how the memory thing works in these sequential circuits and characterize the sequential circuits. Okay, as I told you, the main element that is used for sequential logic in digital circuit, it is the flip-flop. Do you know what is the main trait of the flip-flop? Okay, two main traits.
That it has its output stable on the edge.
Okay, not on the edge. So first of all, the D flip-flop, it's a synchronous component, okay? So it has this synchronization signal, which is called clock, okay? So this is the first. The second thing is that it changes only on the edge of the clock signal, okay? What do you mean on one of the edges, okay? What is the edge of a signal, of a digital signal? Let's be more specific.
the time when it changes from 1 to 0 or from 0 to 1.
Exactly. So the moment that it changes from, let's say, 0 to 1 or 1 to 0, it is called the edge of the clock signal. Yeah. Okay. Which is the positive edge?
From 0 to 1.
From 0 to 1. Okay. And the negative edge from 1 to 0. Okay. So basically, the D flip-flop, okay, the truth table for the D flip-flop, it has the input D, the output, let's say Q, and it also has the synchronization signal clock, okay? So if it's, let's say here, Q of T plus 1, okay. So if it D, and I would just, so most of all, it's mostly related to clock. I have deleted the D. So if the clock is constant 0, which is the value of the output Q T plus 1?
Q of T.
It's Q of T, okay. If it's 1, again, it's Q of T, okay. And you all want only the change from 0 to 1 when Q of T plus 1 becomes what?
D.
Becomes D, okay. So basically, you have the clock edge, okay. And during the clock edge, the output changes its value, okay, or it may change its value, okay, because if the previous output was 0 and D is 0, of course it doesn't change its value, but it may change its value. It may load the new value of D, okay, and in this case it's on the positive edge of the clock. By the way, do you know why clock it's called synchronization signal, and why these signals which have clock are so called synchronous?
Because there exists a time when the output is stable.
No.
And
Okay, so let's say you have 20 registers in your design, okay, and all are connected to the same clock input, okay. Actually, the moment they load the value, it is the same, okay, because they are connected to the same clock input, okay. They load the new data, they make their update, okay, when it is the positive edge of the clock signal. So actually it's at the same time, okay, because that positive edge occurs for all the registers within the design at the same time, okay. And actually the clock signals ensures this kind of synchronization, okay, so that all registers will load their data at the same time. Okay, so that's why clock is called synchronization signal, and that's why you have synchronous logic, okay, because you load into the memory element, in this case into the registers which are composed of D flip-flops, okay, they are loaded at the same time, okay. So I'm gonna have the design for the code for the D flip-flop, okay. Let me put something like this. The output Q. Also, you have, I'm going to make, in order to keep things simple without reset, okay. So, okay, this is a trivial example, but you're going to use. So for each register within the design composed of D flip-flops, okay, you have two signals. This is the output of the register, and this is the input of the register. Usually, I know from also from industry, they are denoted _reg _next. Okay, so actually the register D has composed, in this case, it is composed of one D flip-flop, has two signals. One is for the input, D next, which is called the future state or the next state of the register, and this is the input, and the _reg, which is the current state of the register. Okay, so just let me, I told you. Okay, so I have this declaration of two signals. And this is the block, the always block, which describes the sequential logic. Okay. And this is the reg. Here, assigned Q equals 0. Okay. Okay. So this is the code for the flip-flop. Okay. Questions? Okay, so I'm going to put a question. What is the event in the sensitivity list?
The rising edge of the clock.
The rising edge of the clock. So actually, as you can see in this always block, it's inactive all the time except the rising edge of the clock. So basically the dreg, okay, this dreg, which is somehow the output of this always block, that dreg is constant, okay, or is stable all the moments except the rising edge of the clock. So on the rising edge of the clock, the dreg actually becomes the next. Okay. What I would like also to emphasize a big difference when you model sequential logic, use this non-blocking assignment. Okay. I will have, for example, next course, I can have an explanation about why using, and it's especially when you use sequential, use this kind of non-blocking assignment, when you use combinational logic, use this blocking assignment. So do you see the difference? Yeah, this is also a very log specific thing. Yeah. Okay. Questions? Okay, so try to model an 8-bit register, parallel in, parallel out. and try to make a share. Okay, did someone finished? Has anybody finished? Okay. Okay, so how many inputs and how many outputs did I say?
8.
8. So it's parallel in, parallel out. Okay. This is the parallel in. This is the parallel out. Okay. And okay. So this is the code. Yeah, so basically you have 8 flip-flops, okay, connected to the same clock signal, okay, and which, of course, the 8 flip-flops are loaded at the same time. They have the clock signals, and at the same positive edge, you load the clock signal. And basically, this declaration here and this always block, it's how you model. Okay, this always block may have, and I will discuss in the following minutes. This is the way that you model sequential circuits and the sequential block in all, no matter how big it is your design. Okay, so if you have, let's say you have 3 register, let's say you want to add a 16-bit register called A. Let's put it like this, declaration, and 12-bit register B. So the sequential block, it's like this, yeah. Okay. Okay. So this is how you model sequential logic, basically. Yeah. Okay. So let's pass to the next thing. Reset. What reset does? So what reset does?
Resets the value of the
What
output.
means the reset, the value of the output?
Clear.
Okay,
Makes it
actually,
zero.
Zero.
the formal definition is that it puts the output of let's say a sequential element to a known state. Okay, the most used known state is of course 0. Yeah. Do you know what's the difference between synchronous reset and asynchronous reset?
Asynchronous reset is in the list, the sensitivity list.
So coding, yes, but what does it mean?
It means that whenever the reset changes its value, then that moment, the
Not changes, it actually means that any moment reset activates, in that moment it will make the sequential element go into node state. Okay, so that's the asynchronous reset. It does not matter where regarding the clock signal, where the clock signal it actually is. You activate the reset. Let's say you put the reset on 0, and the sequential element in that moment becomes 0. Yeah. For a synchronous reset, it's actually when reset happens only on the positive edge of the clock signals. Okay, in this case, and the code, it's actually, let's say we activate reset on 0. Again, this means that direct becomes 0. Reset, it's a priority kind of signal. Okay, so this is for the synchronous reset. For the async reset, okay, because reset it's active on 0 here. What do you have here? Have the neg edge. Okay, you wait actually when the reset goes to 0. So basically you check where the reset has activated, and if the reset has activated, you reset the sequential element. Otherwise, you're performing the one on the clock. Okay. If you have questions till now.
Wasn't there a convention for active low elements or inputs to have appended _b or something
Where?
in the name?
I know cases of this, but I have used this way most of the time, so no problem. Because, for example, if you have something like this, usually I have a list of defines, okay, because they are boards which are connected to an active reset on 0. They are boards which are connected to an active reset on 1. You know what I'm saying? And I usually have a define, okay, something like this. And in this case, it's okay, something like this. I usually wrote. Okay, all right. Did you understand? Because
yes.
I usually have this defined. Usually, I have the defined file. Okay, for the entire project. Because if I want to port from one device to another, and the reset it's not active on that board on 0, either have on 1, you know, I don't want to change in the entire code, okay, the entire project. And also for clock and reset, it's not a good idea to make any changes, okay? So you do not act on clock and reset with conventional logic. You don't have any kind, so it's just input clock, input reset, and you leave the design as it is, okay? You put it postage of clock, you don't have clock equals to whatever, okay? Good. Questions?
I have a question.
Yes.
It would be wrong if instead of using dreg and dnext, we would make a q reg and we would sample it directly in the always block.
No, but actually what I'm giving you here an example, it's as an example, okay, this is trivial. Okay, so we're starting from trivial things, but I'm thinking about the future things, okay? When you have multiple registers and so on, okay? When you want to scale. Okay, so it's this is just a convention, and it's also made to have more tractability of the code, okay, or readability and so on. You can name the signal as you want, okay? It doesn't matter. You know what I'm saying, yeah? Okay, but also when you write code in some form of programming language, and you name classes and so on, you don't name, okay, you don't put variables with your name, for example, okay, or classes with I don't know, whatever name. So nobody, at least even if you don't comment that class and so on, you don't or variables, you try to have, you know, that the name tells something, okay? This kind of writing code, it's more about readability, okay? So just an example, and okay, these 3 examples, I would like you to simulate on your own, okay? So to have a little bit of hands-on experience. I'm going to have a simple, okay. So let's have a very simple counter which counts. I'm giving you 1, 2, 3, 5, 7. Okay, and then it goes to 0. Okay, so I have this counting sequence. Okay, so let's see how count prime. Okay, these are the prime numbers. How many bits do I need for the for counting this sequence?
3.
3. let's say like this. Okay. I'm going to have reset. Okay. Usually the counters do not have inputs. Okay, so J just count. Okay. Output, let's say we have this count out. Okay. So I have the counter register. Okay, and I'm going to use count reg, count next. Okay, and I'm going to declare, let's say I'm going to use synchronous reset.
Isn't that register on 4 bits?
No, yes. Okay. Try to use when you have if, force, and so on. In the case of Verilog, to use begin end, even if you have an instruction. Okay. I know from my experience, okay, I have colleagues which have actually lost 1 or 2 days because something like this. Okay, and then you have the instruction, okay? And then he wanted to add something new in this for, and he wrote something like this. Okay, so he lost 1 day, okay? Because the correct way would have been, which would have been the correct way? This was C++, actually. Which would have been the correct way to write these 2 instructions?
Use
Here.
blocks of scope to determine.
Yes. So instead of this, okay, this was the it is the correct. He wrote like this because he wrote the first instruction without the begin end in the C value. Okay, so that's why even if you have 1 instruction, no matter the programming language, you should use the begin end variation. Okay. So count reg equals to 0, and as count reg equals to count next, and this is actually the sequential part. Yeah. Now you have a combinational part, which the combinational part in this case, it determines the next value. So this combinational part actually will compute the input for the sequential part. Okay, so the input for the sequential part, it is count next. Yeah, and where you determine count next? In the combinational. Okay, which is the input for the combinational block?
Count reg.
Okay, it's count reg because, for example, you compute the next value based on the current value. Yeah, so that's why the current value should be as input and the output should be the next value. So count, or is it count reg? Okay, as I told you, I'm going to use initialization because here and the case of count reg, okay, so 3b it's, which is the value for count next?
5.
Now it's 1. So basically, if you're in state 0, you're going to
Sorry, I
enter.
saw a 3 there.
Okay. If you're in state 1, you're going to enter in which one?
State 2.
State 2.
Can't we use decimal instead of binary?
Okay.
I mean, probably it's easier, right?
In 3, count next it's
5.
5. In 5, count next is
7.
7. And in 7, count next is
0.
0. Okay. Yeah, and the default value is, let's say there is some form of event, a fault event, and the current reg goes into 4, sorry, into 4, which is not on this thing, which is the default value.
0.
It's 0. Okay, so you see here, actually, whatever happens, you have this 0. Okay, good. Okay, assign count out. It's so actually the way when you're designing digital logic is to think, okay, what are the current values of the registers and what are the inputs, what are the will be the next values and what will be the outputs for the current values, because this case actually this does these things. Okay, inquires which is the current value of the count reg. Okay, and based on it, it computes the next value of the count reg. Okay, so this is actually the how you design. What are the current values of the registers and of the inputs of the circuit usually, and which will be the next value of the registers and the outputs of the circuit. So this is the entire thing. Okay, questions if you have.
This is a Moore machine.
Excuse me?
This is a Moore machine, not a Moore.
Not quite more, because more it's a counter, you don't have actually inputs here.
Yes.
Okay. It doesn't matter if it's Moore or Milli, the design is highly similar. Okay. So you don't have any differences in the design. Okay. So we're going next week. I'm going to go into more details about the RTL, the 2 segment. This is a first example. I would like you to try the example which I have given you today, and we'll meet for the lab in this afternoon and for the course next Thursday. Okay, so next week is the 3rd week, and we'll have it only on Thursday. Okay. If you have questions. If you don't, we're going to meet this afternoon at the lab. Okay, thank you.
Thank you. Goodbye.
Have a nice day. Bye.
Have a nice day.
Bye.
Okay, bye.
Thank you. Bye.
Goodbye.